we demonstrate attack and defense on Modbus TCP and HTTP protocols in an industrial control system network. Here's our schedule. First, we briefly introduce the industrial control system network. Then, we perform attack and defense on the Modbus TCP protocol and HTTP protocol. Here is a concept map of an industrial control system network. We have the OpenPLC red one. It is a programmable logic controller known as PLC. The green one, SCADA-LTS, is a human-machine interface known as HMI. The Kali Linux is a Linux distribution used to deploy some attack tools. The blue ones are all SDN components. The OpenV switch is OpenFlow compatible switch. The OS is an SDN controller. In practice, we use SCADA-LTS to monitor and control the OpenPLC, and we have Kali Linux to attack this connection. And we have SDN components to deploy countermeasures against the attack. We deploy the whole ICS network in the GS3 server. In this network, 4 zones are presented: core zone, data center, DMZ, demilitarized zone, and outside. 2 firewalls separate these zones from each other. The firewall has a mechanism called security level, ranging from 0 to 100. 100 is most secure, 0 is the most untrusted. By default, all traffic originates from higher security level can access the lower security level. But traffic from lower security level cannot access the higher security level. It will be dropped by the firewall. We place the OpenPLC here and SCADA-LTS here. To make the SCADA-LTS connect to the OpenPLC, we need to deploy some access control lists in the firewall to allow the traffic from this direction. I will show you how the SCADA-LTS can control and monitor the OpenPLC. Here is the web interface of OpenPLC. And this one is the web interface of SCADA-LTS. We place this here and place this here. You can see that the converted temperature is monitored, displayed here. The set point 40 is here. The heater is in auto on mode. Let me change it to manual. It is now in manual off mode, and OpenPLC is also changed. We turn the heater on. The OpenPLC is on. Turn the heater off, and the heater is off. We can also set the point. Currently it's 40 degrees. We set it to 100. Then the set point become 100. we have two Kali Linux to attack this interaction. To defend the attack, we have 4 open-way switches. The open-way switch is deployed in the links so that all attack traffic will be inspected by the open-way switch, and action can be made based on the inspection. We have here the OpenPLC, the SCADA-LTS, the Kali Linux, 2 of them, the open-way switch, 4 of them, and the ONOS. The ONOS is deployed in Docker containers, and the open-way switch connects to ONOS via the Docker 0 interface. We show the Docker 0 interface via this command, docker network inspect bridge. We can see the bridge name is Docker 0. We have here the subnet. The submask length is 16 and gateway. Here are containers. We found our ONOS Docker container, and we have the IPv4 address. Next, we perform attack on Modbus TCP protocol. To deal with that, we use these 2 Kali Linux to attack the OpenPLC. Currently, the network is normal. We can use SCADA-LTS to control the OpenPLC. Let me turn it off. Then we try to use Kali Linux to attack OpenPLC. This attack is a kind of injection attack. When it starts, the OpenPLC will be turned to manual on mode. It means that all the lights will turn green. We target the OpenPLC with the frequency of 20. The attack begins. You'll see that the OpenPLC is positioned into manual on mode, and the SCADA-LTS would see it. But when SCADA-LTS trying to turn the OpenPLC off, it will not work. Trying to turn to auto will also not work, because the OpenPLC is currently in a denial of service, and it is flooded by the commands from an attacker. We will stop the attack. We can now use SCADA-LTS to manage it. It turns to normal again. How the attacker is implemented? We can see it by capture using the Wireshark. We see that the SCADA-LTS and OpenPLC exchange information via the Modbus TCP protocol. And most Modbus commands are read holding registers, read codes, like that. But when we want to change something, we want to control something, like to turn the heater on. It will then produce a write command. This is the write single register. We have here function code write single register, reference number 5, data 0001. This is to turn the heater on. We have also a menu command. This is write single register with reference number 4 and data 0001. This is to turn the OpenPLC into menu mode. So, if the attacker first sent this packet to set the OpenPLC into menu mode, then it sent the heater on packet to turn on the heater. If the process are done respectively, then the OpenPLC will be placed in a denial of service mode. Here is the source code of the attacker. We can see that in the main method, we have a port 502. This is the Modbus TCP port. And here are two packets. This one, write single register command with function reference number 4 and data 0001 is to turn the OpenPLC into menu mode. And packet 2 with write single register reference number 5 data 0001 is to set the OpenPLC into heater on mode. You can see that first a TCP socket is created and initialized with the Modbus. Then we go to send packet 1 and send packet 2. The sending are done respectively. It is in a while loop so that the sending will occur non-stop. First is this one. Next is this one. The packet are sent alternatively to cause the denial of service of the OpenPLC. We will try to capture the packet. We will start the attack. Write single register command is produced quickly. It is reference number 4. This is 5. This is 4. This is 5. The packet are sent alternatively. In this way, OpenPLC is in denial of service and we cannot turn it off. Okay. So, how to defend the Modbus TCP attack? We use these 3 Open switches to inspect all the Modbus traffic sent to the OpenPLC. Because the location of these Open switches, all the attack traffic will at least go through one of them before reach the OpenPLC. Our basic principle is to mirror all the traffic through open switch into the ONOS and let the ONOS SDN controller to decide which is the tag packet. Here's the flow chart of the ONOS app to defend Modbus TCP attack. We have here the packet processor, and there the frequency analyzer. In the packet processor, every packet come in, we will decide if it is an Ethernet packet. Then, if it is an IPv4 unicast packet, then we will decide and select a TCP packet. And then we will decide if it is a Modbus packet. This is done by inspect if it is targeting the TCP port 502. In other words, if it is a request to the OpenPLC server. Then finally, we will choose only the right packet, the Modbus packet with the right single register command that we saw before in the Wireshark capture. Then all the Modbus red packets are logged into a concurrent hash map. And this log I inspect every 1 second. For each IP in this bunch of packets, we'll analyze if it has sent more than 10 Modbus red packets to the OpenPLC. If the packet is more than 10, then we can deploy some defense flows to block the IP. If not, we will not deploy any flows. After this judgment, we will empty the data in the concurrent hash map for the next loop to decide. We will look at it in detail. This is the source code. We have here the packet selector to inspect all the packets. We decide if it is the Ethernet packet. Then if it is IPv4 unicast, then a TCP. And we have destination port 502 and the payload, an instance of data. Then we have the Modbus packet. And we choose to log the IPv4 address, the source IPv4 of the Modbus write packet. This is the Modbus traffic monitor, the analyzer, to decide if the number of packets exceed the threshold. The while loop is sleep for Modbus monitor cycle, namely 1 second or something. And the whole hash map is inspected. If some IP have sent more than 10 packets, then some defense flows will be deployed on all the OVS open switches to block the app, the IP. Finally, the log is cleared before use. let us see the effect of this countermeasure. First, we activate the app. To see if the app is really activated, we should inspect all the flow table in each Open switch. This is done by issuing this command. Okay. The flow entry is correct. Then we set it OpenPLC to off mode and start the attacker. We choose a frequency that is larger than the threshold so that the countermeasure will definitely work. The attack started. You can see that all lights turn green, but now we can safely turn it off, turn it on without problem. The attacker is blocked. We can see that the log in the attacker is all sent without the receive. You can see that there's no response because the attack packets sent was dropped by the OVS. We have here the drop packet. You can see that this flow entry have the highest priority to inspect all TCP traffic with source IP of the Kali Linux and destination TCP port 502. The action is drop. So it will drop the traffic effectively. You can see that now it cannot start the injection attack because the TCP handshake is dropped. This is for the Modbus TCP countermeasure. Now, let's focus on the attack on HTTP. In the HTTP attack, we focus on a slow HTTP denial of service attack called the slow loris. We use this one, Kali Linux, to directly attack this SCADA LTS, to attack its web interface. To defend it, we deploy this Open switch to inspect all the traffic, all the HTTP requests to the SCADA LTS. What is a slow loris attack? From the source code, we see that this is the main function. First, we have the victim's IP address and the number of all connections. The slow loris attack is done by establishing as much connections as possible and periodically send keep alive requests to these connections to keep these connections alive. In this way, a server is suffered from millions of alive connections and its CPU is overheated. In this way, it is called a denial of service. You see that first we create as much connections as possible. We init the socket and log the list of socket. Then we enter a while loop to do the iteration. This is to send keep alive request to these alive connections to make it keep alive. We inspect the slow loris iteration method to find more clues. Here, after some period, it will send keep alive headers to make these connections alive. From the list of sockets, it will send a header. We're trying to do the attack. And it's called slow HTTP test. We have the help here. We use this one, default modes, to send slow headers. The values we should change is the number of connections, C, and the interval between each keep alive headers set, and the connections per second. It is the establishing rate of the connection. And the second, timeout for new HTTP connection. And finally, the URL of the target. Before start the attack, we should change the SD into normal mode. Now it is in normal mode. We then want to trying to capture the attack packet. To make the capture feel cleaner, we will basically just stop the Modbus. Now the link is more cleaner. We'll start the attack. Use the slow loris. We give it 100 connections with the minimum connection establishing rate, and we send keep alive headers every 10 seconds. We use 60 seconds as the server timeout. Our target is a HTTP connection. Restart it. You can see that some connections is established while others are pitting. Now we have 50. Now we have 20. We will apply the filter to make the results more cleaner. We'll only inspect the HTTP request targeting the SCADA LTS IP. Here's a pattern to be identified. That is, we have some GET requests known as TCP segment sent in a very short time. The sending time of them are very similar. What is that? From the source code, they are the send header. They are produced by the send header method to renew, to keep alive the established connection. We decided to further inspect the timestamp value of these keep alive headers, and we found that the timestamp value of them are all the same. They all have the same timestamp value. The unit is millisecond. Why is that? Because they are sent in a for loop without pause. Because the modern CPU are very powerful, so that the command in a for loop will be executed all within 1 millisecond. So all the timestamp of the keep alive headers are all the same, because the difference are too minimum to be identified. This provide an obvious characteristic of the slow loris attack. That is, a bunch of packets with the same timestamp value. You see that now it is 100 connected. And the keep alive headers would be 100. Now we focus on the defense on the slow loris attack. We deploy an open vSwitch here to inspect all the traffic. Based on our current observation, we inspect all the packets and found HTTP packet with the same timestamp. We will focus on the packet with same timestamp and log them. Since the slow loris attack is very slow, we give it a long analyze time. For each IP address, if there are more than 5 packets with the identical timestamp in one cycle, Then we will deploy some flows to block this IP. And finally, in the end of each cycle, we will empty the log data. Let me show you in the source code. Also in the packet selector, we use the destination port 880. It is the port of SCADA LTS. This is to separate the HTTP request. And we only inspect some specific TCP flag PSH plus ACK. This is only for HTTP GET post. You can see this from one command. This is a GET command. You can see in the flag push and ACK. It is 18 in hexadecimal. We change it to decimal. It is 24. Given that, we will log this packet. Then here comes the HTTP traffic monitor. After each long cycle, we will first inspect if there is some packet with the identical timestamp, and we can count the number of this packet. If the number of packet with the same timestamp exceeds the threshold, we'll deploy some defense flows targeting the IP address. And finally, we'll clean the log. Now, let's try to defend the attack. We start the guard application. Now we're trying to get the lower connection number so that the test will finish quickly. We have 10 connections. The connection is now established. We now have 10 connected. Let me see now. Yes, we have. We now have the defense flow that with the highest priority targeting TCP packet with the source IP of Kali Linux, test TCP port of 880, actions drop. Now the attack is automatically stopped because there are no open connections left, because all the connections are dropped by the open vSwitch. We will want to start it again, because now we already have the defense flows, so there are no connection, and the attacker is exited very quickly. All the connections are pending, and no connection is successfully connected. So the defense is effective. Here's the end of this video.